Good morning, everyone. I would like to introduce our first speaker, Arinze Nwokolo. He's an assistant professor in the Department of Accounting, Economics, and Finance at Laos Business Schools, Pan Atlantic University. His work focuses on development economics, corporate finance, political economy, behavioral, and organizational economics. And he will be talking about gas flaring, agricultural productivity, and labor relocation.
Okay, thank you very much. I don't know whether you can hear me. Okay. Wow. Okay, that's right. I'll try as much as possible. Okay, so thank you very much for the introduction. So I'm going to present this paper on gas flaring, agricultural productivity, and labor relocation. So just a bit of motivation to the paper. Now, gas flaring is a global concern. There's a lot of emissions coming from the fossil sector, the oil sector. And the recent report by the World Bank actually said that in 2024, the global gas flaring was about 151 billion cubic meters. Now, if you translate that to carbon monoxide, that is about 389 million tons of carbon monoxide in the world. And that is also equivalent to 46 million tons carbon monoxide in methane. And you see that the same problem also occurs in the US. There's a lot of gas flaring from the oil sector there. And there's a lot of red flag that methane actually affects climate, and it might actually be one of the worst contributors of climate change in the world. And the question now becomes, who are the top countries that are flaring gas? And this was one of my first surprises, because I was thinking Africa should be like number one, right? So I kind of saw Russia and then US. And then, of course, in Africa, the biggest is Nigeria, as you can see there, and followed by Angola. So that kind of led me, okay, if in Nigeria we are kind of the biggest contributors of gas flaring, so what is happening in terms of farmers that are close to these gas flaring sites? So what I try to do is to look at a natural experiment. And what the idea here is, in 2010, there was this act that was passed by the Senate. It's called the Local Content Act. The idea is that to move most of the production of oil from the multinationals to the local companies. And how they did this is because in Nigeria, you have the onshore production of oil and also the offshore. So the multinationals, almost all of them went offshore, and they sold all their onshore assets to the local companies. Then what didn't happen is, by selling all these onshore assets to local companies, what we now saw is a huge spike in gas flaring, as you could see from the graph, that before the Local Content Act, it was almost like stable. But then by the time you had the Local Content Act and the local companies moved to the onshore and started producing more, it spiked up. So what we try to do is, what is the impact of this spike in gas flaring on agricultural productivity of farmers? Just a bit of a context. Now, you have at least about 2 million households close to every single gas flaring site. And most of these households depend on farming and fishery for their livelihood. So you could actually see that kind of impact. So our research question is simple. What is the impact of the gas flaring on crop yields and agricultural labor productivity? And whether the farmers actually mitigate the economic losses that they face from this gas flaring, being exposed to gas flaring, and how do they do that? And we look at two mechanisms. So what happens to labor allocated to agriculture versus service sector? In economics, we always talk about the structural transformation, farmers moving from agricultural sector to the service sector. And then is there also an impact on air pollution? All right. So I will not bore you a lot with the contributions to the literature, but the idea here is, in the literature, we see that the structural transformation, most of the things that we have seen, at least that has been studied, is that the reason for that is low intermediate inputs, and also self-selection of low ability workers, size of the distribution of the farm, and also climate change. So what I try to contribute here is, what I see actually is gas flaring makes farmers to allocate labor to the service sector, especially if they are exposed to gas flaring during the harvest period. But then during the planting period, even though they're exposed, they still go ahead to plant. Reason being that if we do not plant during the planting season, then I have nothing to harvest. Okay, so it's almost like this kind of push commitment mechanism that during the harvest period, I go to the service sector, but during the planting period, even though I'm exposed, I still stay to plant so that I can have something to harvest. So in the institutional context, so in Nigeria, I'll show you just in a brief about with the map. Where you have most of the oil production is where the place we call Niger Delta region. And in that region, you have a couple of 9 oil producing states. So Abia, Akwa Ibom, Bayelsa, Cross River, Delta, Edo, Imo, and Rivers. And most of the companies that are producing the multinationals like Shell, Exxon, Chevron, Total. Now, these companies, as I mentioned earlier on, have moved now to onshore. So they have sold almost 90% of their onshore assets to the local companies. And then we see that there's a lot of high cost of environmental and health hazards in the communities that are around these regions. So this is like a map of Nigeria, also showing where the gas flares are. So the red dots are where you have the gas flares. Now the blue dots are where you have the farmers. So these farmers are the geocos of farmers from the LSMS data of the World Bank. And then the buffer zone that you see is like 20-kilometer buffer zone. The reason behind that is in the LSMS data, they always have this displacement that they have done, that if you are a farmer within the rural area, there's a displacement of 10 kilometers. So you don't know exact location of the farmer. But if you're in the urban area, there's a displacement of 5 kilometers. So in order to see whether we capture them very well, we now use 20 kilometers, which is also something used in the literature. So if you also look closely, see that in addition to the map of Nigeria, I've actually kind of focused more on the southern region where you have a lot of the gas flaring. And you see the amount of gas flared and farmers affected across the 3 waves of the LSMS data. Now, we use the 3 waves because the first wave was prior to the Local Content Act, and also because the gas flaring that we have, especially on a monthly basis and also a geocoded basis, started from 2012. So that is why we can see from the second wave to the last wave. So if we now look at the data sources, so most of the data sources that we use came from remote sensing data. So the first one on the gas flaring comes from Nostra in Nigeria, and they use various satellite data. Then we also use data on monthly precipitation from the Climate Research Unit. The same thing, monthly air pollution data on such like black carbon particulate matter, sulfur dioxide, and nitrogen dioxide came from Giovanni, which is available at NASA. We also use, as I mentioned earlier, the 3 waves of the Nigerian Living Standard Measurement Survey. And the good thing about the survey is the panel data. So that means you are able to observe the same household across different waves, right? Now, just a bit of a caveat here. So in the latest LSMS data, there was a bit of a change. So they actually sampled a different set of households because some of the households they are sampled before were being affected by the conflict in the north. But what we had done is to follow the same household between 2012 and 2019. And these are the households we focus on. So we actually have a panel of these households across these 3 waves. So the empirical specification is just simple, like your diff and diff. The idea is that we kind of look at flares, being exposed to flares, one, during the harvest period, prior to the time of the survey, and secondly, during the planting season, all right, also prior to the time of survey. And then we control for different things, weather controls, household fixed effects, because we have a panel, and region by month and by year fixed effects. And everything is clustered at the local government area level. So it does the same thing at your district level clustering. So what are the results? So one of the things we see here is there's a huge impact in terms of crop yield. So actually see like a 66% decline in crop yield being exposed to gas flaring during harvest time, and also like a 69% decline in labor productivity. Also when you're exposed to gas flaring, farmers are exposed to gas flaring. And we see most of this impact comes during rainy season. right? So the 69% decline comes through the rainy season, and 50% of that in the crop yield also during the rainy season. If we look at the mechanisms, we see that the households actually move from the agricultural sector to the service sector. So there is about a 9.3% increase in amount of months worked by the household in the service sector. And also the number of weeks worked is about 19%. The household dedicate more time to the service sector in terms of weeks worked. If we also look at this from the perspective of the actual amount of time dedicated by households in this sector, so in terms of hours worked in the agricultural sector, we see a decline by 10.5%, and also weeks worked declined by about 39% in the agriculture sector. Now, this is a planting season. We have seen for the agriculture sector, the farmers dedicate more time to the agricultural sector. And that is between 23% for weeks worked and also 9.8% for months worked. Then we also see the same thing happening here in terms of the actual amount of time dedicated to the agricultural sector. So I need to move a bit fast. So this is the last results. This is air pollution. So we see like an increase in nitrogen dioxide, sulfur dioxide, and black carbon in the local government areas that are exposed to gas flaring, right? Which is also like another mechanism that say that with the gas flaring being on the increase in the harvest period, you see a lot of air quality actually reducing, and that affects farmers too. We do not see any impact on health outcomes here, but we do see that there's actually an increase in pollution. So just to conclude, we see that there's a huge impact in terms of gas flaring on agricultural productivity, agricultural labor productivity, and also crop yield. And this causes a misallocation, right, from moving from the agricultural sector to the service sector by the farmers. And we also see that households that are in gas flaring areas are more exposed to high concentrations of pollution compared to the rest. And we see that this is another alternative mechanism that we use to explain the agricultural differences across countries or within countries. And thank you.
Thank you, Arinze. Our next speaker is Rachel Shave. She is a research scientist.
Anytime.
Okay.
Okay. Just waiting for the slide. So I'm presenting a geospatial impact evaluation that looks at the impact of landmine clearance in Afghanistan on economic development. So the motivation behind this work is probably obvious. As we know, landmine contamination is extensive. There's over 100 million mines across the globe. And these mines pose a major risk to life and limb. In addition, they restrict the flow of people and goods. And then they also prevent the productive use of land. And although mines are extremely cheap to place and they're placed at a very rapid rate, clearance efforts are costly both in terms of money and, both in terms of time and money. So right now, over 2 million mines are planted every year, whereas we're only removing 100 to 200,000 every year. And if we stop planting mines today and continue clearing at the rate we're going, it would take us over 1,000 years to clear all of those on the globe. So obviously, because of all these considerations, there's a lot of arguments about prioritization and targeting so that we can get the best bang for our buck. So we might wonder what the literature says about how landmines are impacting economic development. And there's a whole slew of literature that shows that landmines decrease health, they decrease education, structural transformation and consumption, and they also negatively impact public trust and opinions. In addition, the broader literature on conflict suggests that after landmines go away, there might still be a shadow that exists that impedes economic development. So, landmines have a negative impact on economic development. So we might think that clearance will positively impact economic development. But the literature on it is actually quite slim. So there is work in Mozambique that shows that clearing landmines positively impacts economic development as measured by nighttime lights. However, these effects are found with clearance in near transport hubs and along transport corridors, and there's little impact found in rural areas, although this might be because of the use of nighttime lights. In terms of rural effects, a paper in Colombia has tried to supplement this by incorporating test scores and cocoa cultivation, and has found positive impacts on economic development in rural areas using these outcomes. But despite this literature, gaps exist. So as we mentioned, there are just these two studies that use a panel design. And these use very limited outcomes, if any, to look at rural development. And this is important because in our sample, only 16% of our sample is ever lit. And so looking at rural impacts is important. In addition, the studies that have been completed look primarily at post-conflict settings, and there's big reason to believe that the impacts of landmine clearance in ongoing conflict areas is different to that in post-conflict settings. So we'll look at an area that has active conflict. And then finally, although one of the big gains of clearance is that you can use land for other purposes, no study has yet used land use as an outcome. So we'll contribute to the literature by, first of all, compiling a data set in Afghanistan on landmine contamination and clearance. We'll use not only nighttime lights, but we'll use daytime satellite imagery so we can look at the impacts in rural settings. We'll look at land use as an explicit outcome, and then also we'll be able to speak to conflict dynamics in ways that other studies have not been able to. So some background in Afghanistan. In 1979, Soviet forces invaded and started placing the first landmines. Over the next few decades, though, landmines continued to be placed by every force that was in Afghanistan. After the Soviets departed in 1989, the Mine Action Program of Afghanistan was created, but there was kind of a slow process to it starting up. So until 2007, not many places were cleared, relatively speaking, and the process for determining which areas would be cleared and how it would be done was dominated by international actors. In 2007, lots of key reforms took place. So first of all, an influx of funding came about that allowed just a scale up of activity. Then a prioritization of local staff and a decentralization of the planning process happened. Okay, so in practice, what this means is that instead of prioritizing based on potentially like the best impacts that they expected, so targeting cities, they adopted a cluster approach. So they told teams to start clearing in the area they were in, clear all the areas around them, and then move on to the next area. So we're going to argue this helps being like a quasi-random rollout of clearance. And also in practice, it just meant that clearance reached much further than before. So we were looking much more at rural clearance than we were prior to 2008. So we'll focus our study in 2008 and onward to take advantage of this. So our treatment data we received from DMAC is a lot of polygons that look like this. And each one has precise geospatial boundaries and also has the exact date of clearance. And so we can then combine this with geospatial data to our advantage. So this zooms in on Kabul province. And as you can see, the distribution of hazardous areas and when they were cleared is quite diverse. So we have both spatial and temporal variation, which helps with our identification. So for identification, we're going to rely on this idea that there was a quasi-random rollout of clearance activities. Just to be sure, we'll do two-way fixed effects, accounting for grid cell and year fixed effects. There is some anecdotal evidence that because of topological difficulties with clearance, areas that were lower in elevation and slope were cleared first. And in subsequent years, then they would kind of travel up slopes. So we do find this areas cleared earlier had lower slopes, lower elevation, and slightly higher population counts. We'll account for this in all our robustness checks, and we find that it doesn't actually materially change our results. So we believe it's robust even to this. So because of the recent literature on two-way fixed effects, we need to account for dynamic treatment effects. We'll use Callaway and Santana. This is beneficial because it restricts you on the forbidden comparisons. So the first outcome we'll look at is economic development as measured by nighttime lights. Because of the period we're looking at, we would want to harness both DMSP and VIIRS. We'll use the Tang et al. Data. This data is great for two reasons. First of all, it harmonizes both of those lights data sets. And secondly, it's been shown to be particularly effective in areas that are less lit, which is very relevant for Afghanistan. So we see a little bit of a pre-trend in nighttime lights prior to clearance, and the dotted line is going to project that pre-trend forward. But we find actually a large and statistically significant impact on nighttime lights after clearance. And it's actually quite materially large. So by year 5, the effect is about a quarter of the sample mean of nighttime lights. And by the end, by year 8, it's about half the sample mean. So it seems to be the case that in lit areas, at least, we see a significant and substantial impact on economic development. When we look at how this differs by market access, we find that the effects are concentrated among those with better market access. So it seems to be the case that market access is allowing landmine clearance to create the most benefits for economic development. Next, we'll focus on land use data. So as we mentioned, the problem with nighttime lights is it's really only sensitive to areas that are ever lit, which is a small part of our sample. So we use land use and land cover classification from Landsat 30-meter imagery. We do this using visual inspection, training and testing sets, and then maximum likelihood and random forest algorithms. The accuracy is quite good, over 83% for every period, and for the most recent period, over 90%. Because of the kind of time constraints and data constraints, we'll limit to the 3 provinces with the most clearance activities. And we'll calculate kind of land use, land cover every 5 years incrementally. So some examples of what this looks like in practice. On the top left, you have what farmland looks like. On the right, you have what bare earth looks like. And on the bottom left, you have what built up or kind of industrialization and urbanization looks like. And the end product ends up looking something like this. So the land is categorized into a bunch of different categories. And then within each hazardous area, we'll be able to see the percentage of each category. We'll focus primarily on built-up and farmland because we expect the impacts of clearance will mostly be on urbanization and agriculture. So first we'll look at the impacts on built-up. For those cleared earliest, so 2008 and later and 2010 and later, we see a positive impact of clearance on built-up land use. For the later cases, this is not the case. And then when we look at farmland, we'll see in the first period with the earliest cleared, we'll see a positive impact on farmland as well as those that are later cleared. It's not quite significant though. Interestingly, in this kind of middle group, we actually see a negative impact on farmland. One of the challenges of land use, though, as you can imagine, it's looking at the conversion of land rather than the kind of intensive margin of agriculture. So that's something that we think might be influencing our results. So we'll also look at farming intensity, and we'll do that by looking at NDVI. So we calculate this by identifying the seasonal peak for each pixel and then aggregating the mean over the whole hazardous area to get farming intensity. And what we find is there's not much of a pre-trend, but a little bit, and we'll project this forward. But the impact on farming intensity is substantial and significant, far above what you would expect with the pre-trends if they were to be projected forward. So it does seem to be the case that there is a large impact on agricultural productivity as a result. If we look at farms that had below median production at baseline versus those that had above median production at baseline, we see that the gains in productivity are concentrated among farms that were struggling at baseline. And then finally, we'll be able to look at conflict in a variety of ways. We do this using the Uppsala Conflict Data Program. This collects organized violence, and we use 10-kilometer grid cells for this simply because of the nature of the data. So the first thing we'll look at is kind of the effect on clearance. It seems to be the case, although it's not statistically significant, that there is a large impact on conflict, and it's a negative impact, meaning that conflict decreases as a result of clearance. When we look at kind of the types of blockages imposed by the hazardous areas, what we find is that these kind of reductions in conflict were concentrated among the agricultural blockages. That's kind of hard to see, but that is the case. So it seems to be the case that in areas where the hazards, the landmines, were blocking people from farming, conflict was reduced the most. So this suggests that maybe the opportunity cost of conflict was kind of increased, and so in farming areas it was just not as conflict-ridden afterwards. I actually forgot to include one graph, which is one of the more important ones, unfortunately, but we also look at kind of areas that are low baseline conflict and those that are high baseline conflict, and look at the impact on nighttime lights. And we find the greatest impact on nighttime lights is areas with the most conflict, which is perhaps surprising considering when you think about prioritization and targeting, it's typically been the case that people have focused the clearance efforts on areas that no longer have conflict. But we find that it's still beneficial, and perhaps most beneficial, to clear land in areas that have conflict. And then finally, we control for conflict because it might be a confounding variable. And obviously, conflict is accounting for some of it, but we still find significant gains in nighttime lights even when controlling for conflict. So what should you take away? Well, first of all, landmine clearance has a big impact on economic development, even in this setting with active conflict. We find large impacts even in rural areas, even though the literature prior to us had not found these. And this suggests that prioritization targeting should really try to more equitably distribute clearance activities. And in addition, although targeting can be shaped by conflict cycles, clearance itself can reduce conflict, and especially some of these like economic development gains are especially strong in areas with high conflict. So we really think prioritization and targeting efforts should be more equitable when looking at conflict as well. We do a quick cost-benefit analysis, and we find that the gain from clearing 1 square kilometer was approximately 385,000, and the cost was only 92,000, with the break-even period being roughly 5 years post-clearance. So although these clearance activities are costly, we do find that they are, very successful in producing economic gains. So thank you.
Thank you, Rachel. Our next speaker is Eleanor Benami. She's an assistant professor of agriculture and applied economics at Virginia Tech. Her research focuses on environmental and developmental economics, with particular focus and expertise in remote sensing and machine learning. She will be presenting her work on welfare effects of data-driven versus administrative border for insurance zones.
Hi, it's great to see everybody here today. Thanks so much for making your way over and participating. So this work is joint with a number of other people, including Elliot Kirchner, who's at Virginia Tech and soon moving to the University of Wageningen, Andrew Hobbs at the University of San Francisco, Michael Carter at the University of California, Davis, and Zhenong Jin, who was at the University of Minnesota and now Beijing University. And I want to motivate some of this discussion by saying that risk really matters for people's lives and livelihoods, particularly in agricultural environments. And what we see is in the event that adverse weather strikes, a lot of people tend to think about what comes after. And you may see, and decades of literature has shown, that people will remove children from school, and you see this attendant loss of human capital. Some people may skip meals, which can result in nutritional deficiency and stunting. And then we also see some of these decapitalization effects where people can then stay trapped in negative income cycles. But there's another side to this coin, which is in the anticipation that adverse weather can strike, we also see these ex-ante impacts where people may choose local seed varieties, lower value crops, or basically reduce the types of investments they have because they're trying to build up some cushion. So that brings in the importance of having some reliable risk management. So there's this ex post effects of allowing people to recoup some of their losses, stabilizing incomes, and retaining the ability to try again in the next crop cycle. But we also see that that can be quite important for unlocking productivity gains by enabling people to adopt improved seeds, higher value crops, and invest more inputs either through land or labor. And to think about a little bit more the context that we're working in here, we'll be talking a little bit about insurance, and it's rooted in this concept of trying to smooth out production variability. So to illustrate this concept, we're looking at a particular farmer over time and their income, and you see that there's this big dip in the middle of the time period. And when you have well-functioning insurance, it basically provides this floor underneath people. And you can think about this as this intertemporal transfer from good times when your incomes are actually lower because you're paying into insurance to bad times. So when bad times fall, you are able to, again, have this floor beneath you. And in the context of index insurance, which is what we'll be talking about today, it's really important to understand that oftentimes these are pegged to what is happening in a group environment. So here, very conveniently, our group environment here is basically this dark black line. And then when you have some sort of adverse weather event that occurs and you have noted this, then you will receive payouts that reflect the gap in between what is reflected at your group level and your trigger. So that means in this context, the area over which and the people with whom you are grouped together really matters. So to illustrate this, I also want to show, on the in the yellow dots here, this reflects a series of farmers who are not doing particularly well. The green side reflects a series of dots where producers are doing quite well. And what we sometimes see is that these index insurance groups will be defined based on administrative borders. So just to illustrate here, we have our administrative boundary that intersects these groups or bisects these groups. And we ask this question of what happens if you instead try and group different producers who are a bit more homogeneous? Because in the previous case, you might see that that this producer who was not doing particularly well in yellow was overshadowed by the ones who were doing in green because the average favored the green. And on the flip side, you had producers who were in the green who were being paid out who might not necessarily need to have been, which can make things more expensive for everybody overall. So our central question in this work was whether data-driven zones derived from Earth observation and weather data can deliver more welfare to insured farmers than administrative borders, and then at what cost. So we have a couple of different ways that we're looking at this. We have varied the ways in which we define what these agricultural insurance zones are. We also vary the types of information that we use to define what these zones are, the number of them as well, and very importantly, another defining feature of how these area yield index insurance programs work is not only do you have a group structure, but you have people who are going out into the field and they're collecting data. And as all of us who have done field work know, it is expensive to do that. And so there's a lot of questions of how do we figure out how to manage the costs of those while still maintaining a statistically reliable figure that comes out of them. So where a lot of the literature has been, and I think we heard echoes of this a little bit yesterday as well when people were talking about index insurance briefly, is that there's been a huge emphasis on what index should activate payouts. And that is critical. That is a really important part of this question. There's been a variety of different ways that people have done this in the past, going from field-based assessments, which can involve either crop cuts or surveys, weather indices, and then also satellite indices. They all have a variety of different trade-offs. What we found when working with our partners is a lot of them have found weather and satellite indices to not serve their purposes particularly well. And so they still keep going back to these field-based assessments, also because farmers tend to like them. They see people in the field. There's more credibility there. And so instead, we were trying to take a different angle to this question and think about how you basically draw your lines and where you choose your fields. So in this work, we're focusing in on zone definition so that we're grouping producers together so that they are more homogeneous. where we can minimize some of the within zone variance and this notion of avoidable basis risk, where you have this mismatch in between an individual's experience and what's happening with their index. But we also have some ongoing work that I'm happy to talk about at another time that's thinking about this field sampling design. So with limited budgets, where do you send people out into the field so that you can capture representativeness across this group and that central moment as well, and that you get higher marginal value out of where you send people into the field. So how do we accomplish this task? So I'm going to take us to the western maize belt of Kenya. We were working with an organization that had collected over 13,000 crop cut yield observations, and we used these for some of our performance assessment, which I'll speak to here momentarily. This spans about 184 wards, which you can think of as administrative 3 units, and that's the number that had at least one crop cut observation in every year. And then we had 67 sub-counties, which that had crop cuts within them as well. And you can think of sub-counties, if you're coming from a US context, as actually about the county level, so administrative 2. So we have, as I mentioned before, 3 different ways of defining insurance zones. You can think about the first 2 as benchmarks. So first we use administrative data from the Global Administrative Database. And then this is an anchor in the sense that we have 14 counties, and we had what we ended up using was 100 different sub-counties over which you can use to say, okay, if you just use these boundaries and you looked at what yield dispersion looked like and our metrics there, what would welfare impacts of insurance look like? We also then use the yield information to design a series of zones as well. So this is kind of peeking at your data because we call it a benchmark case because it's not something that you would necessarily have available to you if you're trying to design zones ex ante. But they do give you some sort of reference, and they'll come back into play a little bit later on for our performance evaluation. Then we have these agri-environmental indicators. So again, there's no yield data used in these. We only take, for example, EVI, NDVI, temperature, precipitation, soil from soil grids. And we use both the locations of our crop cuts as well as 50,000 randomly selected points throughout our study area in order to then identify and use a clustering algorithm to assign each location to a cluster, and then each smallest administrative unit a ward to its modal cluster value. And with that, we're also able to vary the number of clusters we have. So to drive that home a little bit more, again, we have 5 families of agri-environmental inputs. We look at this in the time period before we had yield data as well, with this notion of saying, okay, you're trying to design a program, what information do you have available to you? So precipitation, we're actually using the decadal here. Precipitation, temperature, NDVI, EVI, and soil characteristics, and a series of different ones from those. And it's, again, we take the values at each crop cut location and these 50,000 randomly selected points that we extract from the 2021 World Cereal Maize Mask. And then we average those into a 2 by 2 kilometer grid. And then we normalize those because they are all on varying scales before clustering. So what this looks like, if you're just using precipitation, is we take this superset of cells that have either our crop cut locations or one of the randomly selected 50,000 points on our maize cropland mask. We assign each of those to grid cells into a cluster, and within each administrative 3 unit, the most common grid cell cluster value becomes that ward's insurance zone. So if you have 100 different points within your cluster and 75 of them are all in cluster 3, your ward will then become assigned to your zone 3. And this allows us to also have information across the full space, because you don't necessarily want to look at just where people have been involved in these programs in the past, but you want to be able to say, if you have a new producer who's joining into these programs, to which zone would they then be applied? We use this notion of risk-adjusted welfare, which for economists you would recognize as a certainty equivalent. I like to think about this as 6 of one and less than half a dozen of the risky other. So capturing this notion that people express some risk aversion for things that are not necessarily, that expose them to some risk. We use constant relative risk aversion utility equation. And the really key point to drive home here is that our notion of insurance value stems from looking at your certainty equivalent with insurance to your certainty equivalent without insurance. And why do we use this measure? Importantly, we use this because it reflects this asymmetric loss function. So if you talk to people who work in the remote sensing space, a lot of the folks, when you're doing performance evaluation, focus on things like root mean squared error or R squared that are really agnostic as to whether you are above or below your trend line. But in our context, where we're thinking about when bad things happen, are people covered? We really care about what's happening in that lower tail of the distribution. And so this allows us to weight those negative deviations more, and basically what makes insurance valuable in the first place. The other benefit of using a certainty equivalent, in previous iterations of this work, we had used expected utility, but it turns out not a lot of people think in terms of utility units, but certainty equivalence allows you to think about welfare gains in terms of dollars, and then allows you to make comparisons across program designs, regions, and audiences in a way that people can understand. So there's some baseline assumptions here about how we distribute costs among policyholders. We do think about this as an actuarially fair product, so there's no additional profit loading there. In all of these cases, there's some additional sensitivities that we run in the paper that I'm happy to speak to as well. So what do we find? So here we're showing on the left-hand side some of our benchmark values of if you're using the yield or your Oracle-based assessment or your administrative boundaries. And then on the right-hand side, we are showing all of the different welfare gains associated with our agri-environmental clusters. For administrative 1 units, where we had 14, we actually see that many of our agri-environmental indicators do about as well, or in some cases slightly better than our even yield-based metric, and do a fair bit better than our administrative units. That changes when you go to more administrative units and go down to the admin 2 level, in part because we think of the high data collection costs associated with going into the field that having smaller zones will imply. So and the other important feature to draw out of this, it looks like the $36 isn't showing up here, but in many of these cases, it's a really large and negative impact that it has, which is unfortunate because that's one of our main conclusions. It's in the paper, and I'm happy to show you the graphic separately as well. But what we also find is that the story isn't just about where we draw the lines, but also how you think about how well are we measuring those losses. So this comes back to how do you design the index and your imperfect average yield estimation, how much you sample in a given area, and the costs of those. So we generate a series of heat maps here that illustrate what happens when you vary the number of zones and the intensity with which you sample them, and then the costs associated with that. So we have this moderate set of costs here of $10 per crop cut. And when you imperfectly estimate yields, which we almost always do, and so you have some design risk, and when crop cuts impose costs on policyholders, we find that sampling intensity actually matters a bit more than the number of zones. So what you want is the stuff that's in the purple range, basically. So that's oriented towards the lower side of number of zones and the higher amount of sampling intensity. And the low numbers of crop cuts can generate outcomes that we see in gray and in red that are actually actively harmful to people. So the importance of using these welfare measures, these programs pay out less than people pay in, even in their most vulnerable times. We also were looking into how much do we change variance as you increase the number of zones, and I think this helps explain some of our results a little bit more. At least in our context, we find that as you increase the number of zones you have, the amount of variance that you're able to decrease actually declines only very little. And in some cases, due to some idiosyncratic variation and this restriction that we imposed of having fixed budget constraints, you actually increase the amount of variance that you have. This might be a feature of our setting. In places where you have more well-defined gradients, you may actually find bigger benefits from more finely resolved zones. So to take some of these main points all together, what do our results mean for program design at scale that we think are relevant to insurers, public agencies, and other researchers? The really, really important one, I do a fair bit of work on index insurance, and I think people assume that I'm naturally inclined to say, oh, index insurance is great. Poorly designed index insurance can do more harm than good. So it's not a panacea. And I think that's really, really critical to think about. The second is that data-driven zones can outperform administrative zones in some cases, and especially at higher levels of aggregation, but that's not a universal result. And it depends on where your administrative zones are and the degree of heterogeneity that exists within them. But the sampling costs and who bears them also really matters. So especially in places that have high heterogeneity, we found that sampling intensity in a zone can matter more than the number of zones, which in some cases I think is a little counterintuitive. People think that the more finely you get, then the more homogeneous it may be. And importantly, for some of our operational partners, high quality public crop cut programs. For example, if you're collecting some of this data for agricultural statistics, that can actually cross-subsidize some of these index insurance programs and unlock designs that might not pencil out or be commercially feasible otherwise. So if you're basically taking the burden off of producers and absorbing that for other purposes. And we do see this. Apparently, the India index insurance program is anchored to subnational scale statistics. So there is some institutional precedent for doing that as well. We have continued some of this work with our partners. They were very excited to see our JDE paper out, and within like a month of it being published, they were already going through our replication files and trying to apply it to their context, which is very exciting to see. And with them, we are also looking at alternative production-centered measures of variability and how well those map to welfare, because they're not necessarily economists who are on their team. They're like, well, we want to use yield information, so can we use variance, or can we use coefficient of variation, and how well does that map to things that economists might view as important. We're also looking at the stability of zones to varying input assumptions over time. Alternative inputs, so either historical yield data or a variety of different fancier yield models. We were very intentionally trying to use off-the-shelf, very easy-to-use things for this to simulate what it might look like to design a new program under operational constraints. And then we're also looking at some additional locations beyond Kenya. So I'm happy to continue the conversation on all these things. And again, thank you for your time.
Thank you, Eleanor. Our next and final speaker is Nikolas Kuschnig. He's a senior lecturer at the Department of Econometrics and Business Statistics at Monash University in Melbourne, Australia. His research interest lies in environmental economics, applied econometrics, and Bayesian econometrics with a focus on deforestation and spillover effect. He will present his work on downstream impacts of mines on agriculture in Africa.
Thanks for the introduction. I'm happy to be here. Let's wait for a second. Okay. Yeah, so basically we're having a look at mines in Africa and effects on vegetation downstream and upstream in a quasi-experimental setting. This is work with my co-author, Lukas Washold, who's at FGW USP, Gustav Bierich and Max Heinze, both of whom are PhD students at Uni Zurich and WU Vienna. Yeah, great collaborators if you encounter them. The motivation, mineral extraction globally is really rising, right? So the mineral demand is rising for the green transition, and economic growth demands minerals to an extent, right? So data centers need a lot of critical materials. The problem is we have very limited information about accelerating extraction, right? So we already don't know a lot about mines 20 years ago, but now that the extraction is booming, we know even less comparatively. So there's an observability gap in terms of locations, where is mining happening, in terms of timing, when exactly is there a boom, and in terms of intensity, so how much extraction is going on. From that, as an environmental economist, we get externalities. These are really hard to measure, and as a result, we can hardly attribute them, right? So we can't make the people doing the extraction pay for the externalities that they impose, and it's hard to mitigate these externalities. So if we think of governable mining, yeah, we have a linked problem, right? So sustainable mining, if it exists, has a measurement and identification problem. What are the impacts, and where do we attribute them, and how do we design policy to counteract them? And what we do in this paper is basically tackle a neglected. I'm sorry, the jet lag is getting to me. Externality on food systems and vegetation, right? So we know that mines have these impacts on air pollution, water pollution, but also how does it travel further downstream? So the roadmap for today, I'll try and keep it short, but basically the research question is what's the causal effect, right? So we're really focusing on causal identification of mining-induced water pollution on vegetation and agricultural productivity in Africa. So we're going to focus on vegetation and try and link that to agriculture. I'll show you a bit more background on mining and agriculture in Africa. Then I'll talk about the research design, the sample that we have a look at, mining across Africa, and the variables that we use to answer the question. Then I'll show you the results. And just to highlight, if you want to grab a coffee already, it reduced vegetation health and yields. yeah, it's not ideal. And the next steps is how we close, right? So what are the implications of our findings? What are limitations? What do we want to do next? And for some background, mining and agriculture in Africa, both are really prominent. Mining is a booming sector, basically across the continent, but also very clustered in certain regions. Externalities of mining happen on site. It's not a great place to work. We know there's child labor, there's safety risks and so on, but they also reach far beyond sites. We have a lot of suggestive evidence for that and some causal evidence. One part of it is tailings, right? So if you extract metals, you have to move a lot of soil, a lot of ground. And of the metals that you want, that's only a very tiny part. So you move a lot of other heavy metals that leak in the environment, and you create, basically vast mountains of undesirable stuff. And that enters rivers, affects ecosystems, and causes problems. And then the idea of our paper is, of course, if it feeds into rivers, the pollutants, the issues, the sediment, whatever issues we get, it's going to travel downstream. And this governance gap, where we think of, okay, there's all of these issues. If we are here in Europe, then maybe farmers would have a say, and we would negotiate how the tailings are managed, right? So this is a problem in Germany, France, Italy, Austria, even. But the problem is there's partly missing information, right? So we don't know what exactly the impacts downstream are, and we don't know exactly where they happen. And in general, we don't even know where mining is happening in a lot of places in Africa. And as a result, the external impacts, they're going to be really sparsely understood and measured. And just to highlight, it's a vast continent, and it has very different kinds of extraction. Something that we cover, but we don't fully focus on because of missing data, is artisanal mining. So here in the top right, I'm showing an image of artisanal mining in Ghana. That's quite recent. And that just follows all of the rivers, so along all of the river. So in a sense, that would be the most terrible impact that you can have on the river system. But also it's not one where our design would work because there's no upstream areas, right? So you follow the full river. The other one is a huge industrial mine in the copper belt in the DRC. We also have loads of those all over the continent, and they've been expanding quite a bit as well. For our research design, we just leverage a river discontinuity, right? So in a sense, it's very intuitive. It's enabled by cool data, but the design is very straightforward. So I'm showing you here two mine sites in Angola and the river basin chains, right? So we're tracking where the water would flow if you place down a drop. At -10 at the top for the right mine, that's where we start. That's where the flow starts. Then we go down to 0, which is where the mine is. And we go further downstream. And I'm coloring the river basins here based on the EVI. And that this is the perfect example, right? So none of the others look as great as this one. But upstream of the mine, there's healthy vegetation. Downstream, not so much. And in the right panel, we can then see the cropland masked EVI, right? So we just look at using 2 different land use products at vegetation health in cropland, and we see a sharp drop at the mine site, which our design doesn't identify, but also afterwards, right? So maybe we focus on the 3 basins exactly after the mine, and these are very comparable to the 3 basins upstream of the mine, because the diameter is only 12 kilometers, right? So these are very similar regions, other than there is a mine in between them. We also find suggestive evidence, just to highlight already, that this persists for a while, but here that's not where our causal identification strategy is biting. We also do this for the general EVI. You can imagine there's not just croplands, there's lots of other vegetation, forests, meadows, and so on. These are also impacted, but not as much. And we have a panel, right? So these mines are persistent over time. We track them from 2016 to 2023. If you're worried about that, it also works with subsets, but more statistical power is more better. For our sample, we look at river basins, right? So these are just defined by, I drop water, where does it travel? And then there's one basin downstream, that's the whole design. We have 6,300 basins that are upstream of all mines, right? So they are not impacted by mining. Then 1,900 basins that contain mining sites and 6,100 that are downstream of mining sites. The mine locations we get from Maus et al. which is a remotely sensed product. Or so they have a look at SNL, which is the largest inventory of mining sites and other sources, and they cross-check in 2019 whether the location that is listed there actually has visible mining. They also check in surrounding areas, so they cover quite a bit of artisanal mining, but they also have huge gaps in the sense if you're very worried about artisanal mining. We expand that by a paper for ourselves, so myself and Lucas, where we try and track this over time from 2016 to 2023 and have a look at the expansion of these mining sites over time. It's more of a robustness check, whether the extent is large or not and whether it grows over time, but that's something that we add. And just to highlight, so we see the artisanal mining cluster in Ghana here in the right image. We see lots of mining happening in the southern half of the continent, but something that we don't see here, for example, is mines in Cameroon, the Central African Republic, or in the Eastern DRC, where there's also lots of artisanal mining, or Sudan for that matter, right? So these are not covered by this sample. These are outside of most mine registries. And the basins that we have a look at, we focus on ±3 basins, right? So that they're comparable. We report results for more. And they are 12.5 kilometers in diameter. And if you track the river, quite short, so hopefully comparable. That's what you need to believe. Just to illustrate, this is a mine site in Indonesia, but it's one that's beautiful, and I had the image ready. But basically, we would have the image from 2019 that tells us the extent of the mine, and with our other paper and something that we're working on, we're tracking the expansion over time, and then we say, hey, this mine is active. Maybe this is a bit more important if there's extraction going on, but it could also be, okay, the mine was active 10 years ago, but we still have a huge mountain of tailings that is still washing into the water, and they're not dammed up, they're not contained properly. And our treatment is going to be distance to the mine. We prefer the basin order, right? Because that's the way our data comes in. But as a robustness check, we also have a look at the distance along the river. And there we use a distance decay specification. For the outcome, we have a look at the peak vegetation index. Our preferred one is basically based on the EVI with a land use mask using Sentinel. We also consider other land use masks as alternatives and the NDVI. And we try and go from the remotely sensed product to actual yield data. So I just for calibration and suggestive evidence using DHS and LSMS yields. For covariates that we might want to adjust, we consider elevation, slope, soil, climate, and accessibility to cities as the most important ones. The results are that there's around a 1.3% reduction in general EVI, and that would cover 250,000 square kilometers across the continent and around 1.4 across 74,000 square kilometers of croplands. So that's a vast area, and might look like a moderate effect, but it's also subsistence agriculture to a large extent. So there's a large effect on individuals, but also on production, right? So here we go a step away from the data that we measure. There's measurement error in there, but if we cross-correlate that with production data, it suggests that there's annual losses of 90 to 200,000 tons of cereals, right? So if you compare that to the World Food Program, that is a substantial amount to lose per year. And here's the table, if you care about that. So we have the individual orders, but we also have a look at the pooled one. Thankfully, we get power for all of them. And interestingly enough, a lot of the basins do have croplands inside them. You can roast me on this later on. Suggestive evidence, we see that there's an impact that persists, but we don't want to focus on this because it's not causally identified by our design, right? So if we go very far downstream, you end up at the sea. If you go very far upstream, you're in the mountains. So they're not as comparable, but I think there's a good case that impacts travel for a longer time. We also have a look at heterogeneity. I'll gloss over this, but I can tell you it's not happening in the deserts. That's a good place for mining in terms of vegetation impacts. West Africa is most impacted, which is also where we find gold mining a lot, right? So a lot of artisanal gold mining and mercury use is a problem. Cyanide is the alternative, and it's not great either. And in terms of fertility, right? So fertile regions are more affected, right? So if you have already very healthy vegetation, that would be more affected. We have a bunch of robustness checks, right? So we worry about balance, covariates that we include, how we define the outcome, unobservables, and whether we should constrain the sample to certain years. basically it's a robust finding, I would say. We also check permutations, placebo checks, and something that we want to look into, right? Karen mentioned this, we want to learn about the mechanism. So in a sense, the design says it's the water. So we also check water quality. Measurements are very rare across the continent. So we just have good ones for South Africa, and they're not as good as we'd like. And we see an impact on water quality. So I think there's strong evidence for water quality being the mediator. For the implications, I think we show that there's causal impacts of mining on downstream vegetation. Vast areas are affected, even just in 3 basins downstream. That's just a huge area. In terms of interventions, there's a lot of low-hanging fruit, right? So tailings management is feasible in artisanal mines, and it is definitely feasible in industrial mines. It's actually the one global legislation that worked out for industrial mining, but is still not being done properly. Mercury use has been a problem, and it can be very cheap to monitor water quality on site. And then we can maybe cross-correlate that with more remote sensing evidence. That would be cool. The other one would be to identify affected systems, right? So are these people downstream of a mine? Is there water flow? Are these regions impacted? I think then we could start redistributing. I think what we really show is that we can make externalities more observable, right? So we have a selected sample of mines. We, I think, need to scale up mine monitoring, right? The boom is happening right now. And even in the Eastern DRC or in the Central African Republic, we're not monitoring. We don't know what's going on, but the mines end up in our products. And we have suggestive evidence for far-reaching spillovers, right? So this is one of the dimensions that we show. We don't have a causal, so this is not the same degree of evidence, but it would be interesting to look further into this. And for example, if we know about activity of mine sites, we could get this evidence. As takeaway, I think it helps Earth observation here. It really helps make mining externalities visible and manageable. Yeah, but we need more on-the-ground data to get deeper into this. Thank you.
We have a few minutes for question and answers. So, and we can also continue during the break if you'd like to talk to presenters directly. So please raise your hand and use your mic in front of you if you have that one. Thank you. Okay.
This is a question for Nikolas. That was super interesting. Thank you. Did you say that you took yields data from DHS or LSMS data?
We checked both. We started with DHS, and then the reviewers pointed us to the LSMS. I think, yeah. So we checked both, and yeah, just kind of to undermine that that the EVI is measuring yields to an extent. Yeah. So with LSMS, of course, we have the location shift problem, but I think we looked at municipalities or something comparable.
Okay, so you took measurements from samples within the same municipality and assigned it to the downstream basins within that municipality?
Yeah, I think that or buffers. To be honest, I don't fully recall.
Okay, thank you.
Yeah.
Got a question for Rachel. Really liked the fact that you did this back of the envelope CBA calculation to help understand whether or not cost recovery is possible with the landmine clearance. I'm wondering, because I don't think that you presented it in the analysis, whether or not you're looking at buffer areas outside of the cleared pixels of the polygons. So you'd imagine that there's going to be connected areas that also experience economic growth or some degree of development in response to clearance because they're connected and things sort of grow as kind of clustered or aggregated areas, and that would also affect the CBA calculation.
Yeah, that's a great question. We focus primarily on the hazardous areas. For nighttime lights, it was the kind of 1 kilometer grid cells that intersect with the hazards. For land use, it's the hazards themselves, and then for conflict, it's 10-kilometer grid cells. So it doesn't really get to your point, but that is a good point. It definitely, and I think given that the main findings in nighttime lights are those with better market access, I think it's potentially something that could increase. Yeah, definitely.
Any more questions? Oh, go ahead.
Question on the insurance. So on one hand, it's very interesting. On the other hand, it reminds me a lot of gerrymandering. And there's a power imbalance, right? So the insurers would be able to impact how exactly these clusters are drawn, right? Because mathematically there's no optimal solution. Are you worried about that?
So in the conversations we've had with insurers, they're very keen on a couple of different things. I mean, certainly there's on the one hand, they don't want to have to pay out more than they need to, but on the other hand, they know that satisfaction matters. And you see dynamic effects of if people aren't getting paid out when they expect to be paid out, they're not going to do it again. So there's actually, I think, greater incentive alignment for having a product that works well, especially in contexts when you don't have a lot of subsidies. Most agricultural insurance is highly subsidized, and so producers don't always necessarily see that. And then there's some political economy things to sort out there of who's capturing the benefits of it. But I think we're actually seeing a lot of incentive alignment because they want people to be covered, and then governments are happy, producers are happy, and then they're able to sustain their programs too. Yes.
Okay, so I have actually two questions, one for Rachel and one for Elinor. So the first one is, Rachel, you say that clearance reduces conflict, right? So I'm kind of wondering, does it mean that clearance reduces conflict, or does the conflict reduction allow for you to do more clearance?
Yeah, so I think it's potentially both, right? So the pre-trends of, it's not that in order to clear, they're waiting for conflict to go away completely before they clear, but there is a little bit of a pre-trend, but the impact's way more than we would expect with the pre-trend. So I do think that there is an independent impact, but yes, it's very hard to kind of, yeah.
So the question to Elinor, so you said that the data-driven zones can outperform admin zones. That's one of your results. So the question here is, what's the cost-benefit analysis for this? So I'm expecting data-driven zones to be more expensive because that means you have to go down to collect data, right? They're just using the admin zones.
Well, all of them require some degree of like going into the field and some data collection there. One of the things that we're actually looking at is whether, as you get these like larger and larger zones, if you can start to then look at the marginal value of information from every additional crop cut. So I think that's kind of the next frontier that we're trying to push on there.
Question for you, Arinze, and that question is that, can you talk about how seasonality can affect or has affected crop productivity?
Okay, I think that is a golden question. So seasonality affects a lot of how farmers are exposed to gas flaring, especially when also you have to think about things like wind direction, right? What happens when you have a lot of upwind or downwind? So what we see is that with a lot of upwind, you have a lot of farmers being affected than downwind. And then, of course, if it is harvest season, you also have a lot of impact from the harvest season and the planting season. Now, the other thing that affects that is rainfall, right? So in the southern part of the country, you have a lot of rainfall compared to the north. So with a lot of rainfall, you have a lot of this pollution. So just a bit of an instance. So in Port Harcourt, one of the things that you experience is there's a lot of black soot in the air. So and this comes from the gas flaring. And those gas soot actually stay in the air, and by the time you're outside and you wipe your face, it's actually black, like your handkerchief is black. So that shows that the farmers are affected a lot by the wind and also by the seasonality in terms of during the rainy season, there's a lot of wind. And that kind of pushes it more towards the surrounding areas and they're more exposed.
Okay. Thank you, Arinze.
So I had a question for you, and that was surrounding, you saw changes in labor productivity and you saw changes in crop yield, but did you also see changes in the kind of area itself? So were people moving out of cropped land and towards other types of uses and just abandoning land too?
So because I'm using the panel data, so I actually observe the same households, and I'm sure that I can see them across the waves, so they have actually not moved. But that is a good question because there's always this problem of sorting, so that if people are more exposed to places of air pollution, they might kind of go to other places. I don't see that in the data. But that is a good point. It's most likely that some farmers can actually move, but given the data that I have, I see them still staying in the same place, the same farm.
Yeah, question for Eleanor. So one nice feature of the administrative boundaries is that they're permanent. Obviously, boundaries change, but they're static. The way that you devised your data-defined boundaries was for a period of time. If you restrict that period and you think about like an out-of-sample prediction, how well do those boundaries perform?
That's a great question. And that's something we're looking at with our partners right now. So they're actually using some of the data from 2016 to 2020 and trying to redefine zones for this most recent period of data from 2020 to 2025 when they have work. So come back to me in like a couple of weeks and months, and hopefully we should know more about that. But one thing I actually want to emphasize is I know we talked about it and framed it in the paper as like administrative boundaries versus data-driven ones, but we're still, because of the virtues of some administrative units, that's often where various programs are administered and people recognize those boundaries. We're still anchoring our zones to the lowest level administrative unit and kind of grouping those together. So we're not entirely absent of them, just going down to a finer scale and think about how we might reconfigure those so that they're not necessarily nested admin 2, admin 3 within admin 2. You could have ones that span boundaries.
Thank you, Eleanor. And thank you, everyone. And one last round of applause for our panelists.